Hello, everyone. In this lecture, we will focus on amines, the last functional group for the semester, and we will see how important this chapter is, not only in organic chemistry, but also in biology. So we're going to begin right away. Amines are characterized by nitrogen. The element nitrogen is what gives amines their identity. So we say amines are organic nitrogen compounds. They may react as bases or nucleophiles. So here's an amine. I'll write it on the top first. It's an N with 3 bonds. Those bonds can vary. They can be H's or R groups. Of course, we're going to talk about, we already know what these are, but we'll talk about them further. So here it is, key. The key is you have this lone pair. So again, this is what we're going to study on. Why is this important biologically? Well, amino acids, they have an amine group in them. And believe it or not, this lone pair plays a huge role in biology, in protein synthesis, in transcription, translation, all of those processes. Look how important this lone pair is for such processes. So let's talk about amines as bases. So an amine as a base, and if you know the definition of bases, you would know that a base is a proton acceptor. So you have an acid here. And you know that in an acid we have delta plus and A will be delta minus. You would know that this lone pair is basic in the sense that it attacks this H, and of course the bonds shift on the A. So whatever the atom or group is left over. So therefore, now you have an ammonium with an N, the positive charge, plus, of course, A minus. Notice the lone pair on this. So this is as, if in this case, it acted as a base. And most of the time it does that. Well, let's look at it when it acts as a nucleophile. So you draw the same thing. And here you have an electrophile. And this electrophile, let's say, is attached to a halogen. And you know that this is delta plus. This could be delta minus. I should have used a different color. So you notice that the lone pair is attracted to this, which is an electrophile versus a proton. And now you will have your product where N, oops, what happened here? Okay, I'm not sure what happened here. There we go. So you have your product with E in this case, whatever was attacked, the electrophile added, and of course N is still the plus charge, a formal charge. And here's your leaving group. Very well. So this is a key statement. The chemistry of amines is dominated by the non-bonded electron pair on the nitrogen. In fact, that's the reactivity of nitrogen. It's that lone pair. Those bonds are not doing anything. They are not breaking because, again, it's very basic to begin with. Nitrogen is very basic. Why is it very basic? Well, let's look at our periodic table. If you notice, the electronegativity increases from left to right. So we know the closer you get to fluorine, the more electronegative it becomes. So fluorine is the most electronegative, followed by oxygen, and then followed by nitrogen. So nitrogen is less electronegative than oxygen, which means it has actually a weaker hold on its lone pair. Therefore, if it has a weaker hold on its lone pair, it's going to result in making it a less stable base, which is, remember, the whole point of acid-base chemistry that we learned last semester and we've been talking about this semester. So again, it's less electronegative, meaning that it's going to make it a less stable base. So here, I'm going to write this down. And then I'm going to nitrogen is less electronegative than oxygen, let's say. Therefore, it does not bear the charge, or we can say electron density, as well, resulting in a less stable base. So that's the key here. Okay, let me go back up for a little bit here and show you, just to remind ourselves, what kind of amines you might actually see. Well, you can have right here, I'm going to write this, you can have aliphatic, and you can have aromatic. So aliphatic is like, you know, this methylamine. That's just a chain, or even these. Okay. Well, aromatic are the ones that, remember, have or satisfy the criteria of aromaticity. So we've seen these before, like pyridine, that's an aromatic amine. Pyrrole, as far as I can remember. These are the most common ones. You have aniline, so on and so forth. So again, you have plenty of aromatic amines. So let's go down to the nomenclature. And I know if you have this electronically, you may increase the space and write it down or on another sheet of paper. Again, we can never predict how much space you need, but I do write big, especially with this program. So we're going to need to adjust. Very well. So let's talk about nomenclature. Nomenclature. So you have primary amines. So what is the primary amine? Well, a primary amine is just attached to one R group. That's it. That's primary because you only have one R group. Anything, an alkyl group, whatever it is. So that's one problem with this program, is that it does not recognize, not like a pen or paper. So what's an example? Well, let's just look at the systematic, okay? So we have something like or even something simpler. Okay, here's how you name it. You find the longest chain and add the suffix amine. Find the longest chain and you add the suffix amine. So in this case, we have one. Okay, it's not letting me type here. Or just count them. You have 1, 2, 3. We know 3 is propane, but since we have an amine group attached to it, what we need to do is add the suffix amine. So if we had this, that would be called propane. What we have now is we're going to remove that E and replace it with amine. So this will be called propane amine or propanamine. That's the systematic name. Now, some of those systematic names are not used. Some of them are not used. You can do another simple one. You know, you have a CH3 and then an H2. Well, that comes from methane. So we call that methanamine. Now, some of those are, like I said, not used very widely. So let's look at some of the simple or the common names. What you do is you name the alkyl group and you add an amine. So for example, when we did this one, this is a propyl group. And then you add, and this is called amine. So it's just propylamine. Or this. So this is methyl. And this is amine. Now, notice that I'm only talking about primary amines. I'm not talking about secondary, tertiary yet. So all of those have just an R group, one R group. That's it. Okay. Now, let's talk about what about ones that have a chain, but they have, you know, substituents attached. Well, let's do that. So let's say we have this. Okay. How do we name this? Well, you follow the same rules that you've used before. Find the longest chain, number one, containing the, or, you know, where N is attached to, and then write the name. So let's begin. we count from the top. So it's going to be 1, 2, 3, 4, and then 5. Okay. The question is, what is attached? Well, at 3 we have chloro. So we're going to say 3-chloro. And then you have to indicate where the amine is attached. So it's attached to which carbon? So it's at 2. So we say 2, and what is 5? If it was just an alkane, it would be pentane, but you say pentanamine. That's all it is. If you have more chains, bigger chains, more substituents, you add them. There is nothing else that you can really discuss other than this. So let's actually talk about now the secondary amines. So what are secondary amines? Well, they have 2 R groups attached to them. Here's 1 and there's 2. 1, here's 2. So secondary. Okay. So let's talk about those. It says the longest chain is numbered, as we discussed before, and then each alkyl group bonded to the N atom is named as N alkyl group. So this is very important. All right, so let's actually look at an example here. All right, number 1. You have to ask yourself, is this a primary or secondary amine? So we know that obviously there's an H here. It's not shown. All right. So this is a secondary amine. Here's an R group. It's a methyl. And there's an R group. It's attached to the backbone. So you have to count just like we did before. So we start from here. 1, 2, 3, 4. Again, it has to be the longest chain and N is attached to it. Good. So then how do we name this? Well, first of all, we have to ask ourselves, what is attached to this N? Well, this is a methyl. Now, if you were to just name this 4-butanamine, because that's what it's going to be, you are going to miss the methyl. If you were to add the methyl, just say, okay, methyl. Well, where is it going to go? So the only way to safeguard against any confusion is to actually use an N. So you say N methyl. And then you have 2. That's where it occurred at, 2-butanamine. So it has to be given the N, because again, that ensures that we're going to know that N, this nitrogen has a methyl attached to it, and we're indicating it here. Otherwise, if we add a methyl, we might confuse the reader that it's attached somewhere there, and it's not. So again, the N ensures that you have a methyl that is attached to the N, and the reader will understand that very easily. Okay, well, what if you have something else? So let's actually look at this here. I know they can occur, as you can notice, that there can be a branch here. So we're not going to belabor this. We're just going to do a few more examples. What if you have a tertiary? I know I didn't include it here, but a tertiary Well, you have N with 3 R groups. Okay, one of them will be the chain, but then you will have NN. Just to make you be aware of that. Yes, for every substituent that is attached to the N, to the nitrogen, you have to include an N. Okay, so what's an example of that? Here we go. Okay. How do we name this? Begin with the longest chain. So you go 1, 2, 3, 4, 5, and then 6. And that includes, by the way, the amine group here. Now, let us actually show that. So you have to write, okay, let me actually erase these two because we're going to do examples on these, but I just want to show you this. Begin simple. All right, so you have 1, 2, 3, 4, 5, 6. Very well. So what do you have then? Okay, so what you have is, let's say, ask yourself, what groups do I have attached? I have a methyl and I have an ethyl. Now ask yourself, how do I name this? Do I name it, what do I write first? Well, ask yourself. It's alphabetical order. So if you have methyl and you have ethyl, you know that the ethyl is going to come first. Okay, so let's begin. Then we write N ethyl dash N methyl. So we have 6. But before, where is that amine occurring? It's at 3. And then 6 is hexanamine. That 6 indicates that it's hexanamine. So, and what do you have? You have a tertiary. So you can tell, even without drawing it, that this is a tertiary because you know you have 2 substituents and then you have the long chain attached to the sample or to the compound. And these are very common. Yeah, what about, so what about, what if you have what if you have N as a group? Okay, well, I'm going to write it down here as a substituent. If you have an amine, let me write this down. Amines as substituents are called amino. So once again, if you have a substituent, that's your amine, then that's called an amino. Very well. So what if you have, let's say, some kind of a sample here where you have the amino as the group. Okay, so let's show you an example. Okay, so you might be asking, okay, well, which one gets the priority? Well, to make it simple, amines are actually on the lowest level, on the lower level. They're lower than alcohols too. So they, in this case, they act as a substituent. So, okay, so you ask yourself, well, how do I name this? So you say, okay, 1, 2, 3, 4, 5, and 6. At least to make it simple for you, they're lowest than all the functional groups we did this semester. They are the lowest. So you have NH2, that's called amino. And it's occurring at 2. So we call that 2-amino. And I don't know if you remember, you should, that this is called a ketone, which is called cyclohexanone. Cyclohexanone. Mm-hmm. Very well. So once again, if it's a substituent, you name it that way. I know we're beyond the nomenclature, but I still want to add some things. I know I should have increased the amount of space, but you should be just add this on a sheet of paper as we always talk in class. The question is how do you actually name them? How do you name them as what if you have a tertiary as a name? So okay, here's an example. Okay, I have to use black so you can see it. And let's say you have a carboxylic acid right here. So let's actually look at this. Here's how you would name it. So remember, with carboxylic acid, you give the carbonyl carbon number 1. So we have 6 in this case. So that's going to be hexanoic. We know that. But the question is, how do we name this right here? Okay. Well, it's a substituent now. So what you should do is, first of all, you should ask yourself, what are these? These are amine. These are methyl groups. But then this is what you need to do. So we can do that. So we can say, okay, N, comma, N. If we have 2 methyl groups, that would be dimethyl. Notice we're mentioning it just like when we did the number, you have to write it twice. Dimethyl. As a substituent, that's called an amino. Okay. Now, the only thing you have to do before you continue is the following. You have to indicate where this whole thing is occurring, and we know that that's at 2. So what you need to do is the following, just like basic chemistry. You put this in parentheses, and you say 2-NN dimethylamino, okay? And then what? Hexanoic acid. I want you to look at this because this is very important. Okay. The other thing that I wanted to mention before we really get to the last two parts of this chapter is what we call ammonium salts, because you need this. You're all going into, or majority of you going into the healthcare field. And it's interesting, it's important to talk about those. So ammonium salts are where you have N has 4 bonds, and those are usually R groups. And we call it R4N plus. Why are they important? We're not going to name them, but one way of naming them is just simply naming them in alphabetical order. If you have multiple of them, you have 2 methyls, let's say, and an ethyl, so on and so forth, you can you can name them. But I'm not worried about the naming. What I need you to do is just familiarize yourself with those. The reason why they're important is because pharmaceutical companies, they often use, or they name amine salts by naming the parent amine followed by the name of the acid used to synthesize the salt. What do I mean by this? Well, for example, if you have this, okay, so again, this is called, so you have ethyl. I'm not requiring you to know this, but I just for your interest, dimethyl ammonium, because the N with 4 bonds is ammonium chloride. And then you have, so you have amine hydrochlorides, oops. So you have amine hydrochlorides, where they have an HCl attached to them, or they have an amine. Okay, it's just not writing very, let me see. Hydrogen sulfate, which is, with H2SO4. That's obviously from when you use sulfuric acid. You'll notice that these are common with the pharmaceutical names. Now, we have 2 reactions to worry about for this lecture, so it's a very small lecture. But before we do that, I wanted to, or we can actually do them and then we can come back to this. So let's actually look at 2 important reactions, very common in pharmaceuticals for amines. Number one. And by the way, you should be able to know how reactions are of amines or amines are prepared. They can occur by a nucleophilic attack, something like if I have NH2 minus, I can attack and then, get this. So that's one way of making amines, right? Substituted amines. But we already talked about that. We want to talk about two very important ones. Oh, I jumped to the reductive amination. My apologies. So let me actually go to the Gabriel synthesis. So the Gabriel synthesis of amines is needed because you need to avoid, right? What it does is it avoids polyalkylation. Okay, because they're very strong nucleophiles. They can keep, alkylating, adding basically, or more than here, more than one alkyl group. So it avoids polyalkylation. So this is only one, reacts only in a single nucleophilic substitution, and then it's done. It's not done, and it doesn't have any nucleophilic nitrogens. So that's the idea. So here's how it looks like, the Gabriel synthesis. So the Gabriel synthesis first begins with, and this has to be drawn very carefully, you have Rx, so that's an alkyl halide. It's very electrophilic. And then you have a very unique base this base is called phthalimide. Ion. So notice here it is. It's nucleophilic. So what does it do? Attacks the R group, kicks out the X. So then the next step is now the R group is attached. Still have those in there. Now, what does it do? It undergoes hydrolysis. We talked about hydrolysis. And by the way, if you're going into the medical field, please remember this reaction. You will see it a lot. So this is hydrolysis. It's basic. It's a basic hydrolysis. It's to replace, to get rid of basically the amide and replace it with the carboxylic to make it carboxylic. So what's going to happen? Well, look at these bonds here. This one, pay attention there and there. You're going to break these bonds using this hydrolysis reaction, and then you're going to get the nitrogen out, the amine out on its own, the amine on its own. So this enables you to produce R NH2. So in this case, it's a primary amine. Plus, of course, these, and I'm going to draw them out. Which is what remains. So we talked about basic hydrolysis. Be aware of this. And we said that the basic hydrolysis gives us the carboxylate version of the molecule of the compound rather than the carboxylic. Carboxylate is when you have a negative charge on the O. It's a conjugate base. So this is what you get, and here's your amine. You made your amine. So let's look at a reaction and how do you, so this is the pretty much a mechanism. Make sure you know it. And then let's look at a real example. So if I give you this on the test, if I say, okay, this is a, it's just it's not moving very flexibly. That's why this this pad is not as I expected it to be, but it's better than nothing. So you have a lone pair here, negative. We know we have another one there, but we're concerned with one. So if I ask you, okay, give me the product. All right. Here's what you have to do to draw the product. To draw the product, all you have to do is take this N, kick the Br out, and attach this alkyl group to the N. Basically, the attachment now is going to be between this carbon here and the nitrogen. So that's the attachment via a bond. So your product would look like this. Now, if I give you, say, okay, here's the other step. If I give you this as just one step, that's what you would give me. But if I give you this, where you have the hydrolysis next, then all you have to do is get the amine out, or the nitrogen and its alkyl group out, and then you form the amine. Here it is, the primary amine, plus the dicarboxylate here. As that. It's always the same outcome. So again, work on that. You'll form basically an amine. If essentially at the end, this is going to replace the Br. If it undergoes the complete reaction, meaning the hydrolysis. So basically, anytime you see an alkyl halide, all you have to do is remove that halide and replace it with the NH2. That's it. Okay. The other reaction, the final reaction, is called reductive amination. Meaning, what you need to do is you need to make an amine from aldehydes and ketones. From aldehydes and ketones. Very well. Now, there are other reactions in your book. We already examined these in terms of how to prepare amines and amides. So those are already, we examined in the last few chapters. So again, that's how you would make amines, amides, and you reduce them. Now, what we need to do is just look at novel, new reactions that you haven't seen. That's our task here. So it's a two-step process method that converts aldehydes and ketones into primary, secondary, and tertiary amines. So let's look at the step one. So the step one, it says it's a nucleophilic attack of NH3 on the carbonyl group that forms in this case, an amine. Remember that, an amine, which is not isolated. Okay, so let's look at step one. So let's say this is an aldehyde or a ketone. And it's drawn this way to help you actually, or we can draw it the other way to help you see it. So remember, if we have ammonia, we make an imine, not an enamine. That's a different story. If you recall that. So that's the first step. And this is your amine. Go back to chapters 21 and 22, especially chapter 21, and you'll see this reaction in there. That's a nucleophilic attack. So what is step two then? Well, step two is a reduction. You reduce this. So what happens is you take this and you reduce it. And when you reduce it, you make okay. It's just an amine. Remember the definition of reduction? More carbon-hydrogen bonds. So here we added a hydrogen bond. Less carbon, nitrogen, oxygen, or halide bonds. And in this case, we formed the amine. Amine. So let's look at an example. What do we use for this? Well, we use the following reagents, but let's look at an example. Okay. NH3. And then you use something called sodium borocyano, borohydride. Okay. So this is sodium cyanoborohydride. This is the reducing agent. Okay, how do I show the product for this? All I have to do is replace this whole carbonyl with an NH2. That's it. Because that takes care of the first step, the attack, and then the reduction afterward. That is it. Now, does it have to be only ammonia? Can you use something else? Of course. So you can make a secondary amine. Okay, let me just. So let's say we have methylamine here. or it could be written as CH3NH2. And then the sodium cyanoborohydride. All you have to do is, again, replace this whole bond with N and remove one of the H's. And then here's your R group. And now you made a secondary amine. So on and so forth. That's pretty much it. The last thing I want to end with, that's it. No more reactions. As bases, we've already talked about them as bases. There's nothing new, that they can always act as bases. So, for example, if I have any acid like HCl or acetic acid, so if I have, acetic acid right here, and if I have NH2, all that's going to happen is this is going to become, here's your conjugate base and NH3. So this is your acid, this is your base, conjugate acid, conjugate base. And we know how to deprotonate by, or at this point. That is it. And the reason why is because, you might want to write this down, is because amines have a pKa about from 38 to around 484. So they're very basic. Okay. How important is that? Well, I don't know if you've been watching the news around us. Of course you have. Who hasn't? You will notice that in the last few days, there was a talk about using some drugs, anti-malarial drugs, to combat the coronavirus, COVID-19. Okay, let's look at that. And some of the suggested ones were hydroxychloroquine and chloroquine. Those are anti-malaria drugs. They're synthesized from what we call quinoline. So this is quinoline right here. It's an aromatic compound. And it undergoes a series of reactions to make hydroxychloroquine and chloroquine. Chloroquine has been made for almost 100 years now. And hydroxychloroquine is more recent, like still an old drug, but it's more recent. They, again, are made for anti-malaria drugs. Hydroxychloroquine is used because it's less toxic and more potent. Okay, how is this relevant? Well, I'm going to preface this by saying that I do agree with the scientific community that we do not know yet, because we do not have randomized trials. I know it was said on the news, people are hopeful, perhaps there's something, but I went and looked up some articles and to talk about them. And there was an article here that I'm going to post on Brightspace. You might want to read, and probably I'm going to have you do some kind of an assignment on it. And this article was written back in 2009, so 11 years ago. And it talks about, the title of it is Antiviral Activity of Chloroquine Against Human Coronavirus. Now, it's probably not the same coronavirus that we're talking about, COVID-19. By the way, the word 19 stands for 2019. OC43 infection in newborn mice. So it says until recently, human coronavirus, H-CoVs, such as H-CoV strain, were mainly known to cause 15 to 30% of mild upper respiratory tract infection. In recent years, identification of new H-CoV included severe acute respiratory syndrome coronavirus, revealed that it can be highly pathogenic and can cause more severe upper and lower respiratory tract infection, which is what we're seeing in right now in the world. It's deadly because of the severe acute respiratory syndrome. Stands for, I think, distress syndrome, ARDS, including bronchiolitis and then pneumonia. Pneumonia is that. To date, no specific. Wouldn't it be nice if we developed something 9 years ago or 10 years ago, but we did not know. Anyway, I'm going to skip to the next one where it says here, so it says that after our results show that the lethal infection in newborn mice can be treated with chloroquine acquired translacently or via maternal milk. The highest survival rate of the pups was found when mother mice were treated daily with a concentration of 15 milligrams of chloroquine per 15 kilograms of body weight. Survival rates declined in a dose-dependent manner, with 88% survival when treated with 5 milligrams per kilogram chloroquine and 13% survival when treated with one. So the lower you gave it, the smaller the survivor rate. Our results show that the chloroquine can be highly effective against H-CoV, OC43 infection in newborn mice, and may be considered as future drug against the human coronavirus. So those are human coronavirus. I know, I believe that those are not the novel ones yet. I'm not sure. I have to investigate, but they do say that there might be something. So you can actually look at the here, and it talks about the SARS outbreak. So possibly, we're still investigating it. The question is, how does chloroquine, or I'll leave it until we have a discussion. But you can look at it here.